it be you journey on to light the day. When the night is overcome, you may rise to find the sun. May it be an evening star shines down upon you.
Go ahead, Joel.
Hello, and welcome to the final technical session of the Applied Superconductivity Conference. My name is Joel Ullum, and I'm the leader of the Quantum Sensors Group at NIST in Boulder, Colorado. I'll be moderating this session together with Sam Benz, also from NIST in Boulder. Our plenary speaker this afternoon is Arthur Lichtenberger. Arthur, or Art, is a professor in electrical and computer engineering at the University of Virginia and director of the UVA microfabrication laboratories. He received his bachelor's from Amherst College in physics and his graduate degrees in electrical engineering from the University of Virginia. His group's research includes the investigation of superconducting and semiconducting materials and microfabrication technologies for new terahertz devices, circuits, and metrology. Together with his collaborators at UVA, he has built an internationally recognized research program in superconducting materials and devices for ultrasensitive single pixel and array terahertz detectors. He has collaborated with numerous astronomical groups, including the National Radio Astronomy Observatory and the Hertzberg Institute of Astrophysics, to make key contributions to the Atacama Large Millimeter and Submillimeter Array, or ALMA, which we will hear more about in a few minutes. He was elected to the board of the Applied Superconductivity Conference in 2012 and will be president of the board and chair of the next ASC conference in 2022. Art is also a founding member, president, and chief operating officer of Dominion Microprobes Incorporated. Art, I'm really excited to hear your talk today, but before it starts, I'd like to acknowledge and thank our sponsor for this session, which is the University of Virginia. In addition, your talk will be preceded by a short video from UVA. Let's begin.
Could you engineer not a machine, not a system, but a future way of life? One that pulses with illimitable intelligence and perpetual energy, where today's challenges are dissolved by tomorrow's solutions. A world where 3D bioprinting lets us replace diseased organs with the press of a button, where every object we touch can sense and send information, making our world safer, easier, and more efficient. Where the sensors and bridges can detect and repair breakdowns in material without human inspection. A world safe from cyber attack with hyper-intelligent systems that find and fix susceptible software code within seconds. Where the structure of a palm tree helps us build better wind turbines and cleaner cities. A world where accidents may happen, but fatalities don't, because smarter test dummies helped us design safer vehicles. That way of life is here, powered by the limitless spirit of ingenuity found within these walls, within the students, faculty, and researchers of the University of Virginia's School of Engineering and Applied Science. The only question left unanswered is, what will UVA engineers do next?
All right, I hope you can see my screen. I'm Art Lichtenberger, and had a lot of fun putting this public plenary together. It started off a very technical talk, but when it became plenary, I sort of shifted gears, and I hope you enjoyed it as much as I enjoyed putting it together. So first, I'd like to give thanks to Lance and Peter and their team for rescuing this conference. The work that they've put in is extraordinary to pull this off so well in these challenging times. So kudos to you guys. I'd also like to thank Peter, David, and Sam for inviting me to give this talk. And finally, thanks to Sam and Joel for moderating it. All right, so what black hole and what superconducting journey? I'm of course referring to the M87 black hole, which was recently imaged for the first time in human history by the International Event Horizon Telescope, the EHT telescope. And this discovery could not have been accomplished without the heart of the telescope, which, from my perspective, is the superconducting insulating superconducting SIS detectors that greeted each photon after its long journey through the heavens. So first, I'd like to give some thanks. So I'm thankful to so many people. I'm not going to go through them all, but folks at UVA, NRAO, University of Arizona, Virginia Diodes, the EHT Group, Arizona State University, JPL, UMass, University Space Research Association, Centennial Conferences, and of course, family and friends. And special thanks to those who let me raid their slide decks, as shown here. All right, and finally, thanks to some of the authors of the many great books out there on black holes. So come back, you want a list, send me an email, happy to provide them. There's so many great books out there. All right, and finally, a shout out to fellow superconducting device fabricators across the globe. We toil away in the trenches, helping make magic happen in the industrial and scientific realms. You know who you are. A little bit about me. I'm a professor at UVA in electrical engineering, computer engineering, director of the newly, almost finished $25 million renovation of the microfab and CAD bio cleanroom. I've been active in the ASC conference for decades. Alan Kleinsasser and I have been putting together low temperature electronics session for as long as I can remember. And also chair of the ASC 22 conference. And so here's my shameless plug on the left. Come with us, come ride the wave in ASC 22 in Honolulu. I have a general interest in millimeter and submillimeter materials, devices, and circuits. So my playground is shown here. Jump to slide. My microfabrication playground centers on high-tech equipment for material development and device and circuit fab to make cool things for a variety of applications, ranging from terahertz metrology to radio astronomy. Tools, equipment, make chips, go into systems, repeat. My other playground is shown here. I especially love cooking, pets and hanging out, big dog pets, and hanging out with family and friends. And I have my own black hole. I got him at home, and I can play with him whenever I want. So what really excites and intrigues me about this work, besides working with the students and colleagues, which is, just a thrill and a gift. So I love grappling with the strikingly absurd scales of the universe, from the big to the small. Being a scientific detective, it's a lot of fun, and the jolt for making connections, and of course the beauty that abides everywhere in the universe. I've been depositing films for 3 decades, and taking that wafer out, glistening, just shiny with gold or niobium, it still gives me a jolt, still gives me a thrill. So why give a talk motivated by black holes? Well, black holes have long since captured the public imagination. We can go far back as the Greeks. Poem Hesiod's poem Theogony. Well, he talked about chaos, the dark void, the origin of everything. Sound familiar? Laplace, famous mathematician in the 1800s, wondered many times, there are mysterious, invisible, and powerful bodies out there in space. And popular culture, of course, has embraced the mystery, ultimate power, and time of black holes, including the iconic Star Trek series and movies, and the mind-blowing movie Interstellar, a favorite of mine. And of course, public culture would not be complete without Homer and The Simpsons. And admittedly, I'm not an astronomer, and you may have heard black holes talks given by astronomers. So why am I giving this talk? Well, as I alluded to earlier, most of the superconducting detectors that made this imaging possible were developed over several decades by engineers and scientists at UVA. So what does that mean for us? Well, technology advancement depends on both the individual and the collective community. So I would like to argue to us, the collective, that our ASC superconducting community shares strongly in this important discovery, and we should collectively celebrate. There's been a long-standing interest in developing commercial products. It's been a theme of the ASC, yet we should not lose sight of the critical impact of our collective superconducting effort on science. It's real, it's breathtaking, and it's just incredible. Radio astronomy, to supercolliders, to quantum information, to health. But why are black holes important to science? So I'm gonna do a little history lesson. We're gonna go and visit some of the first scientists in our journey to a black hole. And let's start with Aristotle. He had a simple and satisfying way of thinking of space and time and our place in the universe. We're at the center of it, right? Life is static and it's all about us. Ptolemy, a bit later, well, we realized there's these planets going around, and what's going on? They must be going around us because we're at the center of the universe. And he came up with models with spheres nested on spheres to try to describe this, until Nicholas Copernicus came around in the 1500s. He had the same technology as Ptolemy, but he crashed our centric universe, world universe for view forever. The Earth orbits the sun. Everything does not orbit us. The Earth orbits the sun. And the sun still must be fixed in space. Something must be fixed in space around us. That's really important. And it wasn't until Kepler came around that who benefited from an advance in technology, the use of lenses and telescopes, and strong funding from the kings. And I will share as a scientist that excellent equipment and great funding are essential ingredients for research. And he realized the orbits of planets are ellipses, not circle, and neither body is at rest, just fundamentally shaking up the worldview. We are not at the center, and the center is not around us. Newton came about 1600s and came up with mathematical terms to describe this. He devised universal rules for gravity. And he benefited from even better technology. First telescope with a subreflector, which he built himself. And he found that the paths were elliptical in agreement with Kepler, and explained the tides and comets. And over time, as scientists tend to get from now and then, we got a little cocky. We began to believe that everything in the universe could be understood, and we had a handle on it. But still, Isaac, he admitted he didn't have an understanding of how the bodies communicated gravity. What was that about? He could mathematically describe it, but he didn't have an explanation of what was really going on. Now, fast forward to John Mitchell, somewhat forgotten in the whole story of black holes. And while most astronomers were looking at planets and comets and just marveling at how well they could describe them, Mitchell was studying those stars. He proposed that the pull of gravity should affect light. And since folks thought light was a particle at the time, he thought, well, there should be some star mass to make the star big enough and light should not escape. And so he didn't call it a black hole, but he was really one of the first people to think in terms of what a black hole could be or might be. And while he didn't quite have all the concepts right, he was thinking about this. And part of his theory of how large the mass has to be had to do with the speed of light. So let's consider that for a second. And this gets back to my love of scales. So the speed of light is 186,000 miles a second, right? It seems really fast. You turn a flashlight on, and as far as you can tell, it instantaneously hits that deer or the next car. It's just really fast. Well, let's do some calculations. Let's think about this. So the time for light to travel around the Earth is a fraction of a second. And the time of light to go from Earth to the moon is about a second. Earth to Pluto, 5 hours. Across the entire Milky Way galaxy, which is, on most nights, that's what you can see, 200,000 years. Time to travel that black hole we're going to talk about, M87, 55 million light years. So, there's a different scale here. Light seems really fast, but boy, the scale of the universe makes the speed of light seem pretty darn slow. So by the 1800s, it seemed to many that the heavy lifting in the fundamental laws and science were complete. We had Newton, who had mastered gravity, so it would seem. And we also had Maxwell, who had come out with theories of electromagnetic radiation light. But Einstein, well-known Einstein, he wasn't so convinced. He wasn't so convinced that Newton's gravity and Maxwell's light theories were compatible. And he was a thinker. He asked questions about what would this look like? What would it seem? Didn't just head to the equations. He asked questions. In this particular question, he asked, how would physics look in different frames of reference? If you're in a car, if you're standing still. And for example, what would you experience if you could travel about the speed of light? Almost the speed of light. Would you be catching up with that? Would that light beam be very slowly proceeding beyond you? What would that be? And after some thought and then calculations, he came out in 1905 with the theory of special relativity. It introduced an entirely new way of thinking of space and time. He proposed basically two things. First, he proposed that the laws of physics are the same for a frame of reference. Doesn't matter if you're moving, doesn't matter if you're at rest. And secondly, and this is very uniquely, he proposed that the speed of light is always propagated in space with the same speed. We call it c. It's independent of the state of motion of the emitting body. These are pretty simple thought experiments, pretty simple assertions, quite the revolution. Let's step back for a second. What was that? How do we digest that? And let's first consider something, situation we understand. So we have a pitcher throwing a ball, and someone else is on a motorcycle heading toward home plate. Well, the catcher measures, say, 90 miles an hour on that ball. It's a nice fastball. Well, the motorcyclist is moving toward the ball, toward home plate. So he measures the 90 minus his speed, 60. So he measures 30 miles per hour. Yeah, that makes sense. We can digest that. But Einstein, when you start thinking about light, that sort of thinking is all wrong. According to Einstein, a person traveling on a fast spaceship and a person on Earth both measure a light beam as having the same speed, And I remember my father, he gave me a book on Einstein when I was in the 6th grade, and I was reading that. And I put that book down in the 6th grade because it just did not make any sense at all. So how can both the spaceship and Earth observers possibly measure the same speed of light? This paradox is solved by acknowledging that time it's relative. People with clocks have clocks that run at different rates. Your clock is not necessarily my clock. What did this do? This made Newton's universal clock basis a myth. Moving clocks run more slowly. And this has been proved. It's not fantastical. It's proven. Einstein then moved to general relativity. 1915, he came out with it. And he had another thought experiment. So imagine being in an elevator as it accelerates upward. I think almost all of us have been in elevators. And you can feel the sort of against your feet, right? And so it feels like the acceleration is pushing you down against the floor. And this is quite like the feeling of gravity, right? Being held to the earth. And so Einstein said, well, gravity and acceleration, they're in some sense equivalent. What would that mean? So he did another thought experiment. Imagine being on an elevator, it's accelerating, a really fast elevator, and you're shining a light out. Well, the person on the ground will see that light as a bending arc of light, right? And so using the analogy that gravity is quite similar to acceleration, he said, well, gravity should also attract the path of light. There's an analogy going on here. And gravity should also make a stationary clock run more slowly. So in Einstein's general relativity, gravity affects both space and time. So what does this look like? So how do we understand gravity in Einstein's world? Well, the planets don't circle the sun because of rotated nested spheres like Ptolemy or invisible strings of force like Newton. They simply follow the true space-time path that's been warped by mass. So mass warps the space-time, and the objects just follow their straight paths within that space-time. Special frame of reference is not needed anymore. Gravity is not really a force, but it's instead a geometrical effect. It's just a reaction to the curvature of space-time. And there's a well-known, you may have heard this before. I'm going to go through it very quickly. Sort of try to illuminate a little bit of how one might think of that four-dimensional reality, because we're three-dimensional beings. Let's imagine we're two-dimensional beings just for a little bit. And we're on a globe, and one two-dimensional being starts off in the equator in one place, another place. And when they start off, they're both in parallel to each other. And they're both following what they think are straight lines to the North Pole. But the closer they get to the North Pole, the more and more out of parallelness they get. It feels like there's some force that's pushing them together. And if you ask them this, they would be devising a force equation to explain this. Yet they are simply encountering a geometrical reality. The important thing to understand here is that general relativity is only needed when strong gravitational effects are involved. You can see where I'm heading with this. So up comes Schwarzschild in 1916, and he considered the case of a non-rotating star with all the mass squeezed to the point. He did his own thought experiment. And by this time, the work of Mitchell had been forgotten. And out popped Schwarzschild's analysis, up popped what's called a Schwarzschild sphere, which we know is an event horizon, beyond which matter and light cannot escape if it's inside. So he was really the father of the birth of the black hole when it comes to equations. And he calculated a mass for it, a radius for it, depending on the mass and the speed of light. And most astronomers and physicists at the time dismissed it as simply an artifact of the math, like dividing something by zero. When you divide something by zero, you feel like you're doing something wrong. Your equations are no longer applicable. Something's gone awry. And besides that, how could mass be squeezed to a point anyway? How could that happen? Well, let's just consider a simple hydrogen atom. If a proton is not to scale an electron, if the hydrogen atom were the size of the Earth, so if the entire atom, think of it as the size of the Earth, how large would that proton be? It's about the size of a city block. It's really small. So atoms are mostly, you push on them and they feel solid, but atoms are mostly empty space, just waiting to be squeezed. So if you look at the Schwarzschild sphere and the frame of references, so we're going back to Einstein and applying it to this sphere, from a frame of reference far from the event horizon, and you're looking at the event horizon, time appears to stop at the sphere. And if someone could possibly, approach that horizon, it would look like they're taking for eternity to cross it. And you realize the magnetic fields are really, really high there. So time slows down. However, if you were on the event horizon and still alive, and you looked back at the universe's time would be moving incredibly fast because you're doing it relative to your clock. Everything else would be going back by eons and eons, millions of years just passing the blink of an eye. But according to your clock, you would cross that event horizon and unfortunately die very quickly. So theories out there, but scientists were not on board. White dwarfs. This really shook up our understanding of the universe. It was the discovery of stars that are hotter than our sun, but much fainter. So how could something be hotter yet fainter and dimmer? How could that happen? Well, the white dwarf must be much smaller than our sun. They are now understood to be star core remnants after a star has completed fusion reactions to carbon and oxygen. So they've gotten a lot smaller, leaving a dense core. And when general relativity was applied to white dwarfs, it changed astrophysics forever. So Chandra, I'm not gonna attempt the first name, Chandrasekhar, asked, what happens if a white dwarf is even more massive? And he did the math. He's a young guy. He did the math, and he found that there was a maximum mass limit beyond which the white dwarf will no longer resist the further crunch of gravity, and it will collapse to an infinitesimal point in space. This is 1931. Well, he as well was not, his thoughts were not accepted very well. He was attacked for more than a decade. It was absurd to conceive this could happen. The university shouldn't, people still thinking that the university should operate how they think, and it just wouldn't work this way. Yet, a Nobel Prize in Physics awaited him in 1983. It wasn't until neutrons, nova, and supernova came on on board that landscape that things really got interesting, and people started to embrace his theories. Well, nova, it's the observations of new intense sources of light that then fade away. So telescopes are getting better, and they're seeing these incredible sources of light, but they're ephemeral. They don't last that long. And it was eventually discovered to be an explosion from the surface of a white dwarf. So you have this white dwarf, which has intense mass, not a black hole, but a lot of mass condensed, and the white dwarf steals gas from its companion star, eventually triggering explosion, sometimes 1 million times brighter than before. And here, from fairly recently, a Hubble telescope time-lapse images of a binary star showing such an explosion. Well, soon after, they discovered supernova, and they're much brighter than white dwarfs. They can be brighter than the combined light of an entire galaxy. And in 1933, Zwicky and Body proposed a neutron star, and neutrons had been fairly recently proposed, which are electrons and protons combined together. And so they proposed that this star was composed of neutrons, compressed by that gravity into a dense neutron core. So they have compressed the electrons and the protons together and compacted them. So it's just neutron upon neutron. And so what does that mean? What kind of density? How do we understand that? And I've put here some calculations of density. Sun is 1,000 kilogram per meter cube, which is about the same as water. Might be surprising to you, but sun's a lot of gas. Earth, 5 times that density. Lead, pretty heavy stuff, 10 times that density. Dwarf, 10 to the 9, right? A million times denser than our sun. A neutron star puts them all to shame. 10 to the 17 kilogram per meter cube. It's a quadrillion more times dense than our sun. Can we understand that? It's unfathomable in some ways. So what if you took all these moons, right? So if you took 10 moons and we compressed them to the size of neutron stars, they would all fit very nicely inside the Empire State Building. A little more time goes by, and Volkoff and Oppenheimer, general relativity to the neutron stars. They assumed no spin, and they found past the critical mass, if that neutron star was large enough, it would continue to compress indefinitely. At that point, space-time is so warped that it is no longer part of the universe. Infinite density, zero volume. Physics unable to explain what's going on inside. Can't even see inside. Right? And these guys, Oppenheimer, they thought the issue was settled. However, the community generally did not still embrace it. They were still disbelieved or ignored. It would be more than 30 years until a neutron star was discovered. However, 1950s was a rebirth and a reapplication of general relativity, and it came as well with advancement in technology. And at first, it was an attempt to save us from the singularity, right? No one wanted that singularity. And they came up with, world's first digital computers, better telescopes, and they tried this and they tried that, and they could not save themselves. Theory and calculation showed, given enough mass, the collapse is inevitable. And this rebirth of emphasis pointed to black holes having a lead role in the play of cosmos. And after the 1950s, things really started to get interesting. And it was a mind shift in some ways. Instead of thinking of it as a death of a star, it's the birth of a black hole. And the more sophisticated analysis pointed to black holes having properties, even though they are inside of the event horizon and we can't see them. They have mass, they have spin, and they have charge. In fact, in some ways, very similar to elementary particles, which is very interesting. And up came the age of radio astronomy. So how do we think of this? Carl Jansky, in 1932, created the first radio telescope at a pretty low frequency of 20 megahertz. And he's looking out at the spectrum. And here I've presented a little bit of a map of spectrum. Jansky is here. We have microwaves, we have millimeter waves as we go to shorter wavelengths or higher in frequency, terahertz and optical. So we're up here seeing with our eyes, and Jansky was down here looking at 20 megahertz and trying to solve communication problems. And this was the birth of radio astronomy, and it led to Robert and Penzias and Wilson and Hewish. People realized the universe was not just made up of stars. It was made up of also chemical signatures to be found and understood. Space was jam-packed with a soup of electrons and molecules and chemistry going on. And that was worthy of study, and it will illuminate the understanding of the universe. So 30 years after Jansky, quasars were discovered. And they were extraordinarily bright, but physically small sources of high energy. You could see them. They weren't the black holes. And radio telescopes and X-ray astronomy were examining them, and they were extremely redshifted to longer wavelengths, which meant they were traveling away at great speeds. Small size, enormous power, early in the universe because of the redshift. And in 1963, they came to be called quasars, but still not a real understanding about what they were. And it wasn't until Roy Kerr did black hole analysis that included rotation. Stars spin, gas clouds spin around them, presumably black holes would spin. So finally someone was able to do an analysis of black holes with rotation. And it was hoped, well, this is going to prevent the singularity of happening. But nope. Space-time swirls around the collapsing, rotating stars as it forms the black hole. And the end result is that quasars get their power from trapping into the incredibly stored energy, rotational energy around the black hole. And here's a picture of it made from the VLA NRAO's image, 2018, showing that's not the quasar, but the quasar's in there and the jets streaming out and the energy emanating. Most sizable galaxies are now thought to have a black hole at the center of their of the galaxy. So they're becoming not so much an oddity after all. So by the 1970s, black holes were cautiously accepted by the scientific community. And many aspects of black holes, of course, are still unresolved or unknown. For example, black holes in quantum mechanics. The world of atoms and fields is governed by quantum mechanics. Energy momentum are in individual quantized packets. There's a wave-particle duality, and there's a Heisenberg uncertainty principle in defining position momentum. You define one well, you can't define the other as well. And general relativity, however, is conceived in terms of space-time geometry, not of particles. So a black hole's infinitesimal position, being without uncertainty, presents problems in understanding. Is there a quantum theory of gravity possible? Are there gravity particles? Right? These are problems that are confronting us. Thermodynamics. Hawking originally calculated that black holes' event horizon could only increase in size in time. And that sounded to a lot of scientists like entropy, like disorder increases in time from thermodynamics. But this implied black holes having a temperature, and temperature implies the release of radiation, yet nothing escapes a black hole. Hence a paradox. Well, on comes Hawking and Hawking radiation, and he leveraged the analysis of atoms to view black holes. He used his understanding of atoms to analyze black holes in this way. And he devised a way for black holes to radiate the rotational energy from inside the event horizon using virtual particles. I'm not going to go into it, but there's a way for black holes actually to shed energy, and it's different from the quasar energy. And this Hawking radiation continues until the black holes stop spinning. A long time, longer than the universe has been around so far. But theory is eventually they're going to stop spinning. So in fact, black holes ain't so black anymore. The Event Horizon Telescope. Why try to image a black hole, right? They're fascinating beasts. There's a lot we don't understand. Well, at the most basic level, and this I have the most affinity to this argument in pretty much all scientific cases, is when we explore, we learn. But to date, the evidence for black holes has been indirect. We've imaged quasar systems on a broad scale. There's a great LIGO talk by Nobel laureate Dr. Weiss in ASC 18 on a black hole plenary 2 years ago. But indirect, we're measuring the effect of the black hole. Can we measure the mass and compare it to theory? Help confirm or deny existing theories? For example, deepen our understanding of how black holes form, galaxies form, and help point us to what is missing, for instance, quantum gravity. So what challenges do we face when imaging a black hole? Well, comparative event horizons. Let's take a look at this. If Earth was a black hole, it'd be about the size of a small coin. If our sun was a black hole, it'd be smaller than the small town of Utashina in Japan. The Sagittarius A Milky Way black hole is about the event horizon about the size of halfway between Mercury and Venus. And M87, it's about 3 times the size of Pluto's orbit. It sounds large, but it's damn far away. So we're going to look at that in a bit. But relatively, they're small from our perspective. And can we also make sense of the masses involved? So the mass of M87 is 2 times 10 to the 30 kilograms. Well, it's about this many cases of wine, this many African elements, 2 quadrillion Earths, 6,500,000,000 suns, Earth suns, or about 0.004 Milky Way galaxies. Yeah, well, we kind of, you might think we can understand it in this realm, but who has an understanding of a Milky Way galaxy? It's just really hard to understand, but they are really heavy and increases now the challenges in imaging a black hole. So if we look at Sagittarius, it's 27,000 light years away, so 66 quadrillion miles. M87 is 330 quintillion miles away, very far. Can we make sense of those distances? M87 is 3.3 times 10 to the 20 miles away. Well, Bezos is a 113 billionaire. So if you were dropping off a penny as you traveled, it'd be a penny for every 3 billion miles. So perhaps he's not quite so rich after all. From Earth to M87, it's about 700 Milky Way galaxies. So back to challenges in the imaging of black hole. So if we think of the event horizon and we think of looking at it at Earth, what angle does it subtend? Well, the M87, it's about 4 times 10 to the minus 9 degrees, right? That's a really small number. That's a really small angle. So they're incredibly difficult to resolve. So how do we make sense of this angular resolution? Well, it's similar to looking at 2 human hairs together across the United States, across the continental United States, or looking at the fingernail thickness seen on the moon. All right, so down to the nitty gritty and challenges. So there's stuff in the way, right? Here's our Milky Way galaxy. Here's the center. There's a black hole, and we're out here, and there's just lots of stuff in the way. particularly since we're all in the galactic plane. Additionally, as you get closer to the center, there's additional increased electron density fluctuations, which causes more interference. But the effect is more pronounced below 100 gigahertz. So if we go at a high enough frequency, we can help avoid that. And there's also scattering from the hot gases surrounding the black hole itself. Can our sensors, we're looking at radio astronomy, can the signals get out? Can we see in close enough to see the black hole? And again, this is expected to be less pronounced at higher frequencies. So radio astronomy comes to the rescue. I could give a whole talk on radio astronomy, but just a snippet here. So radio astronomy is particularly important because it gives us the ability to match known chemical spectra to signatures we see out in space. So we can do measurements in outer space at gas clouds, between stars themselves, and we look at that spectrum and compare it to spectra we know at Earth and say, there's this molecule there or that molecule there. And this in turn helps us devise theories of the universe itself. And in order to talk about radio astronomies, I also have to talk about millimeter and submillimeter wavelengths. So there are peculiar challenges operating in this frequency regime. You have classical electronics, which most people are familiar about, voltages and currents, discrete devices where the length scales are much smaller than a wavelength. The electron inertia is negligible. Electrons do the work. And land of resistors. Quantum optics, we have lengths are much larger than wavelengths. Electrons are way too slow. Photons do the work. Well, radio astronomy observatories, especially where we're talking about for the HT, you have waveforms. You have lengths on the scale of the wavelength. You have the energy of the photon on the order of the thermal energy. You have waveguides and mirrors. So it's a very different world to live in. The radio astronomy telescope has a dish, and to understand the resolution of the dish, you can understand that it's proportional to 1 over the frequency of the dish size. So higher frequency, more resolution, larger telescope, more resolution. But there are additional factors. You have to control that shape of the dish accurately. For the ALMA telescopes, they're controlled to within 25 micrometers. This huge telescope is controlled surface to 25 micrometers. There's absorption in the atmosphere. So if you go to higher frequency, you get less signal. Telescopes can't be also huge. They have to be steerable. And there's a concern about pointing accuracy. So there's a lot involved here. But there's a way out of it. And this is what the HT done and what has been used in radio astronomy before. You combine signals from multiple telescopes. And it simulates not just a large antenna. It's just not that. It's also gives you the resolution as if you had a huge telescope. The baselines between telescopes become the basis of the resolution. You need to correlate those signals together, so you need precise atomic clocks to do so. But here's ALMA again. You can see it can operate as an interferometer with many telescopes tied together sequentially in time. Well, the Event Horizon Telescope took that idea and put it on its head, and they took the following telescopes and they tied each of them, several of them, which by themselves are such telescopes, and they tied them together into one massive working telescope. International cast of EHT scientists. Shep Dolman is the founding director. Picture of folks up front, up top. And really a marvelous idea, which he worked on for decades. To understand this further, let's just talk a little bit about the actual heterodyne radio astronomy receiver. We have telescopes, we have a receiver with itself, and then we have the correlators. And the dish from the telescopes feeds this receiver element. There's a horn that funnels into a mixer. There's an LO, tuning bias, I'll talk about this in a minute, and an amplifier. So what does this mean? Well, to mix is to mix two frequencies together, to multiply them together. And the non-linearity is needed to do the multiplication. And there's a simple abstraction for this. If you take just simple, point in the right direction, two cosine terms, you multiply them together mathematically, and you get out the difference term. That's what we want. If you play two notes on a piano and listen, you'll hear a sloshing back and forth. That's the beat note. That's the difference term. That's what we want. So heterodyne mixing takes the signal that you're trying to decipher, it's at way too high a frequency for you to work on with conventional electronics. You multiply it against a pump, LO, which you can move about to look at where different spectra lie. And the mixer translates this down to the IF frequency. And it does so by maintaining the frequency and phase information, which is also important. And so piano is an example, but you need a device that does this. And a diode can do it. And for many years, semiconductor diodes did this trick. In the 1970s, Bob Mattow at UVA, new faculty professor, and Sandy Weidenrem at NREO, which is headquartered in Charlottesville, they came together and they decided developing state-of-the-art gallium arsenide semiconductor devices for mixers would be a great idea, and indeed it was. And from that, UVA has a long-established track record in supporting receiver and technology development for radio astronomy. Tom Crow replaced Bob as director and spun out the well-known company Virginia Diodes. And I am now director of that lab. All right, so UVA and VDI devices have launched into space on dozens of major radio astronomy and atmospheric studies. A lot of excitement. Let's move along. UVA detectors were used for the first reporting of ozone holes and for the upper atmosphere research satellite for studying water vapor in the atmosphere. Just two examples. Well, we're here to talk a bit about SIS superconducting detectors. In order to talk about that, I need to just dip in. Again, this is open to the public, into superconductivity. So what does superconductivity mean? And I'm concentrating on low temperature superconductivity. But there's a transition temperature below which there's no resistance in the material. It's a bit like magic, right? There's a current density. You put enough current in it and the material will show resistance. And Bardeen, Cooper, and Schreifer, BCS theory, came up with a way to explain this. And one of the interesting pieces is that there's an energy gap involved, similar to a semiconductor energy gap, at least in concept in some ways. And so if we think of this, I'm going to pull a feint of, I'm going to ask for a little trust here. Energy band diagram. So we have energy on this axis and density of states. How many states are available on the horizontal axis? And I'm going to have two superconductors separated by a gap. We'll call that the insulator. And there's an energy gap where you can't have any states. At very low temperatures, most of the states below the energy gap are full. And so if you apply a bias to one side, you will raise the energy and you'll have very little current. But once the large filled state is opposite the very empty state, you will suddenly have a rush of current. And it'll be a switch, it'll turn on. And the scales of this is millivolts and hundreds of microamps. It's one of the most abrupt non-linearities in nature. In section, you have here substrate, one superconductor, a barrier, another superconductor, an insulator, protect it, and a wiring layer. And you can imagine that wiring layer going on and connecting another device and another device and so on. Well, let's look at that IV curve. There's a gap voltage, and it's on the order of a millivolt, a couple of millivolts, and the conductance changes in the order of 100 microvolts, whereas a Schottky diode, previous technology, has about a volt turn on. So a Schottky diode is an energy detector, and SIS junction is a photon detector. It can react to photon energies, and we're going to see that in just a second. So if you imagine biasing one side, again, you have a semiconductor diagram, so density of states, and you're not quite at a high enough voltage to have tunneling across over to the other side, but a photon comes and is absorbed, and the energy absorbed, giving it enough energy to tunnel. So in black, you have a DC IV curve. In red, you have the same DC IV curve where you've just you're shining radiation on it, and those photons produce steps in the DC IV curve, which is just a phenomenal event. It's this photon-assisted tunneling which makes this device a unique detector for heterodyne detection and for radio astronomy. Gain is possible out of a two-terminal device. That was ridiculed at first. How can you possibly get gain out of a two-terminal device? You need three terminals. You need a transistor, but no. in the world of superconductivity, some things that seem impossible are possible. Potentially ultra low noise temperature heterodyne mixing and very wide RF and IF bandwidths. So what also was needed, this was an advancement in fabrication technology. And I wish I had another hour, but I'm just going to quickly go through this. Gurvich came out in early 1980s with this idea of, instead of trying to put two superconductors together with a barrier in between, he would deposit this across an entire wafer. You have one large junction across the entire wafer, and you are then left to make smaller junctions from that across the wafer and use them as you like. So you have superconducting, insulating, superconducting. This is an actual junction where we've done a cross section. There's a wiring layer on top, but you see superconducting, insulating, superconducting. Here's a top view where you have 1, 2, 3, 4 junctions with a wiring layer connecting these two junctions, a wiring layer connecting these two junctions, tuning elements to help the mixer chip work properly. The chip itself, this is actually a chip we're working on for a second generation ALMA. It has gold beam leads, and it's a 5 micron thick silicon chip, so membrane, really cool. This chip goes in a waveguide block. As I said, millimeter, submillimeter is in between light and sort of ordinary, well, I think of ordinary electronics. And you need to capture the radiation in a block where you have a flip side split block, two of them to go together, and you channel the radiation in to the actual device. So the device sits here in the block. This goes into the radio telescope receiver, and the receiver goes into the hub. So there's multiple receivers. This is ALMA, and this then goes into the ALMA telescope to work its magic. So my world in particular is the world of fabrication. And I like to think of this in terms of I think my wife, when I think of my world here. She's an architect, and in her world, as in my world, you can add things, you can take things away, or you can modify them. And in her world, they have hammers. Well, they don't have hammers anymore. Electronic hammers. They have saws and wrenches and so forth. In my world, I have $1 million processing tools. Here's one of the first tools that I built. This is me as a scientist, a PhD student in 1986. My first tri-layer system, and I think this is our 4th tri-layer iteration. A lot of my students and postdocs have built these guys. We have a lot of fun doing that and building things you cannot buy commercially. The world of fabrication has complex tools for dry etching, tools for deposition, lithography tools to decide where you're going to do that deposition or etching. And out from that comes devices, and they're beautiful things to make and image. So these images are from scanning electron microscopes. All right, so what does the SIS mixer playground look like? So we can make devices, right? Well, how do we want to make devices? Well, if we think of a SIS junction, there's a capacitance involved. It's a tunnel barrier. There's a resistance. This has moved, I'm afraid. There's a dynamic resistance. And then there's something called the Josephson current, which we're not going to go into tonight. But you have to balance out the resistance and the capacitance. You have to consider it when you make your device. So the impedance of this device is omega R sub n J C. So it's a product essentially of the resistance and the capacitance. And circuit designs require, they want a resistance on order of 50 ohms to make things work. And for designs at higher frequency, if you think about this, as omega increases, this impedance is going to increase. And we'd like this impedance to not do that in order for other reasons in our design. We need to keep the impedance about the same as well. And so R sub n goes as 1 over A, capacitance goes as A, the area. So we can decrease the thickness of the tunnel barrier, and that will greatly increase the resistance. I'm sorry, decrease, I'm sorry, I have this wrong. Decrease the resistance while increasing the capacitance. And so we can get the impedance we want, but we'll need to make the area smaller to compensate for the difference between how resistance changes and how capacitance changes. to get back to having a resistance that's reasonable. So this is just one of the many considerations we confront, but we must, as we go to higher frequencies, we must make our devices smaller, and we must make the tunnel barrier thinner. It's also desirable to tune this capacitance out to increase the bandwidth of the device. So these sort of considerations, they inform the materials we choose, the barriers that we choose to grow or deposit, the fabrication approaches, and the circuit design. All right, and I'm about 10 slides from being out. So for an example, it's the example I'm most familiar with, well, there are a number of astronomical facilities, instruments involved in the EHT telescope. I'm most familiar with ALMA. So let's look at the ALMA results from all that work. This is back, well, it's a bit old, 2014, but Tony Kerr put this together then, and it shows the different bands. These are all superconducting receivers that are on ALMA. And UVA was responsible for band 3 and band 6. Band 6 in collaboration with NRAO, with Anthony Kerr, Tony, longtime colleague and mentor at NRAO, and Stefan Claude at HIA. NRAO as well was involved by SK Penn. He actually designed the mixer chip, and UVA as well. UVA has also realized band 7 and band 8 mixers that have met ALMA specs, but with different institutions, and we're not on this telescope, but we have that capability. So I did talk at the beginning about the impact of superconductivity in science. It's real and it's breathtaking. And so beyond the HT, there are many other experiments. I could have done an entire talk based just on those, but I'm just going to hit just a couple quickies, right? So very recently, hot off the press, 11/2/2020, New York Times article, Life on Venus? Astronomers see phosphine signals. Well, this was realized in part by using ALMA detectors, the band 6 detectors that are same ones that we made at UVA that are being used in the HT. An enormous project, the Herschel Hi-Fi spacecraft. It's a grand international endeavor. And I must, in these times, I must speak out. International collaboration, more than just USA, is great. It's needed. It's absolutely needed, and it leads to amazing things. And this is one example. ALMA is an example. EHT is an example of this. So the Herschel Hi-Fi spacecraft had a treasure trove of results. This is just one, O2 and C plus detection. It's a spacecraft that went out and did its work in outer space, which is really, really neat. And thanks for Paul Goldsmith for this slide information. But in addition to big science, there's I don't want to call it small science because it's pretty amazing, but small in scale as far as the smaller in scale as far as the funding and number of institutions. And this is an example from Lucy Zeras at the University of Arizona using the 12-meter telescope in Kitt Peak. And amongst other things, she's studying molecular transfer in planetary nebula, where actual components are transferred from one system to another, which is really a remarkable thing to be able to think about and to start mapping out. This is their telescope, and this is their receiver. And this from Chris Groppe, who has done a lot of work originally with Chris Walker, still collaborates with him at University of Arizona. Chris Groppe is at ASU, and he's working at larger pixel count focal plane arrays, so more than one pixel at a time, which is pretty neat stuff. And I've collaborated with him on a number of projects, some of them shown here. So put it all together, this is what you get. We're looking out at the constellations, and here we go. This is using the EHT telescope. This is after an amazing amount of image processing. There are many talks out there. I did not go into that land at all. But you're thinking, well, there's the black hole. Maybe no. This is what they saw. It's the stuff in the way. But there we are. And I have to say, I have friends which are nice enough to ask me about my work. But if I go into too much detail about this or that molecule being discovered, eyes start to glaze over. But when this black hole discovery came out, that's all people wanted to talk about. So what's next? All right, what's next? And I'm just going to concentrate on the EHT. So what's next for the EHT? Well, of course, a next generation EHT, very exciting. More telescopes and a larger baseline for even higher resolution. So let's make the baseline broader and fill in the holes more. Perhaps someday moon and space telescopes helping out. Wouldn't that be marvelous? Even more advanced image analysis and data processing. The thought is to use 2 detectors, 230 and 345 gigahertz. And I'm working with university, my group, along with the University of Arizona, to develop detectors explicitly for the HT in our intent, at least. They will also do more imaging with a Sagittarius A, especially with a 345. And, the hope is to do a black hole movie, not just a still, right? But a black hole movie. And there we go. That's the end of the show. Thank you very much for listening to me. And I'll send it back to Sam and Joel.
Thank you, Art. Really interesting. I don't know if anyone can hear me.
Yep, can hear you.
Okay. Really interesting, comprehensive presentation, simplifying the physics of astronomy and gravity, and covering detectors. Really loved your approach to preparing this talk. We're ready for questions. There was one question in the Zoom chat by Maria Salatino. Nice talk, Art. Not sure if I correctly read one of the previous slides about M87 mass. She thought there might be a typo. The sun's mass is 2 times 10 to the 30 kilograms.
There was a typo.
Okay.
I thought I caught them all because I realized how I put the talk together, went back that I had translated things a little correctly. I'll go back and fix that. But I think it's maybe one place.
No problem. I was wondering if you could talk a little bit about what it's like to be a detector guy working with all these astronomers and physicists and engineers building these big cryogenic systems and telescopes.
Yeah, and I'll start off actually. I didn't highlight cryogenics, but there's a lot of cryomech. A lot of folks doing amazing work on cryogenics, and without cryogenics, the work on it, none of this would have been possible because you have to cool these babies, right? And trying to cool them with liquid helium would be impossible. So there are cryo coolers now. You just plug into the wall, and away you go, right? Ultimate martini someday, perhaps. We'll see. Maybe that's the consumer product in every home. But to your bigger picture, I find it so fulfilling and exciting. I can have my team at UVA. We work on problems that have, we're not just solving a problem to make a widget that'll go into something to do something small. We're trying to make things, improve technology, collaborate with astronomers to tackle some of the frankly, the biggest problems when it comes to mass and distance, in the universe. And it's so fulfilling to an honor really to work with different astronomers. And particularly I've worked with, my group worked with the National Radio Astronomy Observatory, which is in Charlottesville. It's just an amazingly open, warm, they love ideas. It's a real pleasure. It's challenging, right? And Sam, you're a fabricator. You know that world as well. You're always coming up against Mother Nature. You have to have ability to long time scale of delayed gratification. You can take you a month to make something and it won't work, right? And if you try back to the drawing board. And so some of these projects take years to get from A to B. I remember very early on, after a couple of years, we finally made our first just chip. It wasn't a detector yet, it was just a chip. And this was back in, it was around 87 or so. and the IV was beautiful, right? Our first chip, the IV was just amazing. And I was there in the room, and Tony Kerr was there, and Shinko Pan, and I said, "Wow, this is great." And Tony said, "We have to go out to dinner. We're going out to dinner tonight." And I said, "Well, what do you mean? What's the rush?" He goes, "Well, you don't know when your next, jolt of excitement and greatness, you don't know when it's going to come next, and you got to seize it." So there's a lot of that. There's a lot of detective work, delayed gratification, but working on projects that have further science in and of themselves. And that was a theme I was trying to convey, that we as a community, and I'm talking, not just about the scientists and researchers in the trenches. I'm talking about the funding agencies. I'm talking about the exhibitors, right? From Cryomech to Lakeshore, right? To Lesker. I mean, so many people make this work possible, and we all collectively have a claim, and should be really quite honored to be and joyous to be part of it.
I'm going to combine a couple questions together that we've gotten. So I hope you can answer them all together. There's a question about what are the materials that you used, I assume, for the detectors, and where do you think heterodyne superconductor detector technologies are going to head next in terms of frequencies and technology?
Yeah, well, the niobium technology, which was Gurvich, you take niobium, you deposit aluminum, you then take that and partially oxidize part of that aluminum layer and form aluminum oxide. It's all very nicely controlled. Put niobium on top, and you got a great junction. And it works up to 600 or so gigahertz. You can push it higher, but you're starting to have confront the losses in the superconductors themselves. There are now technologies with niobium tinitride and niobium, and I know that's where our band 8 results use that. The ALMA, some of the higher bands are already moving toward that. They have technologies of that in hand. Some of the work to improve ourselves, for instance, in the ALMA world, at band 6, you might have noticed it had the lowest noise temperatures of any of the receivers. We can make it a little lower, but we can broaden it. We can make it cover a larger bandwidth, and we go to higher IF bandwidth, so we can take bigger chunks at a time. So there are things we can do besides just improving the noise temperature, lowering it. There's things we can do to get more information gobbled per astronomy time, and astronomy time is, these are $1 billion. Atacama Array, multi-billion dollar institution. We want to get the most out of it that we can. There is work with using superconductors of higher energy gap on both sides, and in particular, Mike Sibery and my group is working with niobium tinitride on both sides, where we deposit the barrier. We have a new type of deposition, I'm not going to go into, but a new way of depositing, and we feel we'll be able to make high quality all niobium tinitride junctions that can go up well beyond a terahertz quantum limited, which is exciting for us. So there's move to go up in higher frequencies as well.
Excellent. Joel, do you want to ask a couple questions?
Sure. Thanks, Art. That was really a great talk. You covered a tremendous span in time and space.
I'm from New Jersey originally, so I can speak really quickly.
We have some questions from the Q&A, and maybe I'll pull one out sort of at random. Tim Hogan asks, if focusing closer in the universe, could you image truck-sized objects on planets in other star systems near Earth? Can the technology be developed for tasks of this type?
So they could be applied to that, depending on what that object was, right? So the objects we're imaging now are excitations of gas, right? It's energy. So you wouldn't use a radio telescope to look at a truck, right? It's emitting black body radiation, but it would blend in with the moon, So it's not the technology du jour for spying on people on other planets. It's more the technology you're looking at stars, at star systems, at the great soup of interstellar gas and excitations between in the cosmos.
Right. I might ask a selfish question of my own about the famous M87 image. So the luminous ring around the black hole is asymmetric. And I'm curious, what is the origin of that asymmetry? Is it just an accident of what was near the black hole, or is there something fundamental behind it?
Yeah, you and everyone else are very interested in this, and it's a good reason to go on and add more telescopes to EHD and add another frequency band to further explore that, right? So you have to keep in mind, you're not looking at the core of the black hole, the infinitesimal, because there's nothing there to be seen. You're looking outside. You're imaging the gases, which are highly excited, highly rotating. They are magnetic lines of incredible force, which are emanating from the two poles of the spinning axis of the black hole, coming back on itself. And when you have magnetic fields and you have ionization, you have excitation. So it's expected to be crazy there, but they were not expecting, to get such a sort of a bottom-heavy donut, so to speak. So yes, stay tuned.
There's an easy question for you, Art.
Those are the worst, Sam.
How long did it take to capture the M87 black hole by the Event Horizon Telescope?
That's an easy question. I don't actually have an answer to.
Okay.
I'm not sure. It was a lengthy exposure. I think it took longer to analyze the data, however, right? Because you're not taking a picture like you had a camera and out pops the Polaroid. You're getting excitation data. You're getting spectrum. You're getting a frequency transformation of what is physically there, and they went to great pains. And there's a number of great talks about this. Some of them highly technical. Bowman gives several just spot-on talks, but they went to great pains to avoid trying to come up with the final product to look like what they thought it would look like. Right? That's always the tendency, right? The universe must rotate around the Earth because we are the center of the universe, right? So you want to try to keep, as you know, as all of us know, as scientists, you're trying to keep your preconceptions out of it. And there's just a tremendous amount of ingenious ways to approach the data and how to come up and how to test without putting their fingers on it to make sure that they were not tipping the scale in one any direction or the other. And they will be, that took an incredible amount of time and manpower and ingenuity. Yeah, but I can't speak to how many hours of observation went into it. I did claim I'm not an astronomer.
So maybe I'll pull another question from the Q&A session. This one from Maria Salatino. She asks, or she begins by saying, to image the very large, you have to use tools that are very small and indeed pushing to the nanoscale. Do you see sort of challenges in nanofabrication that once met will reap improvements in device performance?
Yeah, so for where we are with millimeter and sub-millimeter waves, so up to a couple terahertz, and given the superconductors involved, so for instance, if devices, my colleague Mike Sivery is working on, if we make an SIS junction with and we've made them with 5 millielectron volts, we just need to get the leakage current down at the higher current densities. If we realize that, we still don't need to make a junction smaller than a couple tenths of a micron in diameter, right? So, and we have that well in hand at UVA and other institutions. So, in that respect, we are not. When we first started off, we certainly were. When we first started off, when I was a graduate student in '81, if you could make a 2 micron device size, of something, you pat yourself on the back and go home very happy. Right now, 2 micron is obscenely large. So as far as this field goes, we don't need to push that further. There certainly are other fields. There's work we're doing at UVA and other places on TKIP devices where you want to make things small and control them over large chip sizes, right? Which is a different thing from just making something small. So there are challenges involved that could be addressed by what you offer up, but not this one in particular.
Thank you, Art. There's a couple more interesting questions. Hong Hai Song asked, could you comment more about international collaborations on important projects? And do you have any specific suggestions to achieve successful scientific achievements together regarding team efforts, financial support for scientists, across different continents? And does it seem that your telescope projects are becoming larger and more international?
They certainly are becoming, a lot of them, larger and more international. And I tried, after I showed the ALMA results, receiver results, I could have shown 30 slides, but I showed 2 slides of large projects and 2 slides of, there's an institution, maybe 2 institutions working together. And so there's still a lot of that. And I think NSF has done a really nice job. NSF has funded a lot of this work in trying to balance the need of the large and the small. So, when ALMA started off, at first it was, my understanding was, at first it was going to be a US project. And then when people got in the same room, they realized, that's just an absurd thing to think about. There's so much money involved. There's so much technology. And this, if anything, is an international project. This should be. And EHT, rode on top of that, using ALMA and all these other observatories. So there's a need for the big science. You couldn't have done EHT. You could not have done that image without such a project. But there's still need for the small. There's the need for the individual PI. Over half my money comes from individual PI grants, or maybe there's, I'm with Bobby Weichel and Scott Barker. We're writing a proposal together out of UVA. Maybe we bring in University of Arizona. Maybe we don't. You need to fund the small and the large, but of course the large takes the lion's share of the money. So there has to be a balance on that. As far as fostering international collaborations, from my perspective, the scientists have that down. So when I wish I was in Tampa, wearing my pirate outfit with Lance, going out to have some whiskey right now. But scientists, we generally collaborate really well, right? We talk to each other. I don't hold back stuff when I'm at a conference and I'm sharing what I've seen, and my impression is, talking to Sam or other people in the field. I've been in the trenches a long time, in particular with folks from JPL like Leduc, and we share stuff, right? And we want to share stuff because and Bruce Bumble, sorry, I'm getting hungry actually, which is hard to believe. We love to share ideas and to throw things on the board, see what stick. So the problem generally is not there. The problem is, if there's a problem, is in government in trying to convince folks that it's worth allocating money for these things, and it's worth doing it over a long period of time, right? You can't expect to fund something for 3 years, something major, and get a result, right? These are, at times decade efforts, right? And they're not, well, you don't have any result for a decade. There are gradations, but the ultimate goal is decade or decades away, and that takes a lot of will on the side of governments and all. I'm not involved in that. That's above my pay grade, at least where I've gone so far. So I talked to Tony Beasley at NRAO and talk to Shep, EHT head, about what dances they've had to do. They're both very impressive people who are not just smart and great scientists, but they speak and they are so convincing, and they hear everything in the room, right? So it takes a special person who isn't just the scientist, but has all those other skills to pull that off. And I'm grateful to have people like that in the community that can make things like the HD and ALMA happen.
Joel, do you have another question?
I do. So in addition to the EHT, there are other sort of powerful tools engaged in the study of black holes. So you mentioned LIGO,
Yes.
which is seeing black hole collisions. And in some years in the future, there'll be the Athena X-ray telescope, which also uses a lot of superconducting technologies. Do you foresee sort of a particularly beneficial interplay between the EHT and those other instruments, or are they sort of non-interacting?
Oh, I hope they interact. Again, that's a bit above my pay grade. I'm not the astronomer, so I'm not in that room. But I would expect that they will be, right. So the discovery of white dwarfs and then supernova, it was done in X-ray and radio astronomy. People put those results together. If the individual PIs didn't do it, someone else in the community would write a paper taking the two data sets and doing it, and then forcing the issue. So I have no doubt in my mind that as we go forward, scientists will talk together and figure that out. And yeah, going forward, that X-ray, it's a huge project and very exciting, and another huge win for the superconducting community.
There's one question from Anwar Abdul Salam asking if in the future could use the same technology in arrays of satellites in space to act as a big single telescope to get higher resolution image. And I don't know if that's what determines resolution, so maybe you can speak to both.
Yeah, so that was on my slide in that they were, where's the HT going? What's next? They are plan is to add a number of different observatories on the planet and fill in the baseline and widen the baseline. But also the question of, you take that a step further, and HT folks are talking about this, putting telescopes in space and on the moon, right? So we have a space force now, the U.S. So maybe that would be a good use for it. I don't know, but I think it's a possibility. It's certainly not the next step that's coming on. It's one of the advantages is if you're in space, you're above the atmosphere, and you could consider going to even higher frequencies, which would, in addition to making the baseline larger, you would be higher frequencies. You would also be improving the resolution. Resolution goes as the area over the 1 over the area frequency. Of course, putting a huge telescope in space is expensive proposition, and populating space with them and not having them hit by space gravity. Space debris. A lot of things to you might have more luck having it all on the moon, but then less atmosphere. But so it's a money issue. I'd be happy to work on it. Sign me up.
Well, what is the next big technology advance? I mean, what are you gonna? Is there something, or the next goal? Is it to do your video of the black hole, or other things?
Well, for the HT, it's to now have 2 frequencies. This is my understanding. I'm sure it's a work in progress and will change as science does going forward and improve and get even grander. But to work at the 345 as well as the 230 gigahertz. To have more telescopes and to improve the technology of tying those results together and analyzing the results, and that is their next perceived step, and that will help up the game for them, so they can. This go around, they were not actually, my understanding, not actually able to say, yes, we've proven Einstein's theory or not within the context of our experiment. They'll be able to push that further. They'll be able to see, like, why is this donut hole, why is it bottom heavy, and what else is there that we don't know we're missing, like, who knows what we're missing. So so that's their next step for sure.
Right. So different detection frequencies with enough spatial resolution, and then you're going to need to get enough photons to do time to do a video.
Yes. Yeah. Well, they have a success, so they can come back to these different observatories and say, you gave us X amount of time, now we want 10X amount of time, right? And I mean, the outpouring of interest and excitement was palpable. I felt in the world, right? Talk shows were, politicians even, right? When they weren't, bad mouthing each other, people were talking about the black hole. So it gives a sense of hope and excitement, and science is real and it does amazing things. I think it could not have come at a better time, and I think it will continue to garner support.
Joel?
Bert, how's your stamina holding up? You've been speaking for a long time. We have one or two more.
I know you're hungry.
Q&A, but if you're wearing out, we can stop.
Dinner has been ordered. It's not coming from the Ivy Inn in Charlottesville, and it's not going to come till 8 or afterwards. So I'm going to stay on and then go to the after party for a bit. So I'm fine. I could talk for hours.
Well, let me pull.
Don't want me to do.
Let me pull one more question from the Q&A, which got a couple thumbs up, and it's from Dmitro Abramov. Is it beneficial to put a radio telescope behind the Van Allen radiation belt to avoid noise, he asks?
Well, yeah, so that gets to the question that you all asked earlier, in that if we can get above the atmosphere, and we certainly get some benefits from that. Radiation itself, the frequencies that is happening is not such a concern for these radio telescopes. So we certainly don't point at the sun. It used to be if you pointed at a sun, you burn out, the detector I built or someone else built. But the radiation belts themselves are not so impactful to the research we do. But getting above the atmosphere is important. So if you think of just consider your hand, it is coated with water. You can put it in front of the fan, I don't care. It has layer upon layer of water. Water is everywhere in our atmosphere, and thank God. But it attenuates and distorts. So you look at stars and they twinkle. It's the water, right? The stars aren't twinkling. Sorry, sorry. That's why you have, for instance, SOFIA, which is a NASA program where they fly telescopes up into space, almost into space, depending on your definition, and then circle in a manner that they can be looking at the same place for a duration, and avoid that, and do work at higher frequencies and observe. At most of the sites on the Earth, there's only a couple weeks or maybe a couple of months where you can observe at the higher frequencies, because those are the only months it's dry enough.
Art, thank you so much for the excellent presentation and discussion. Joel, thank you for his introduction and excellent questions. We want to thank all of the people who asked questions, and we're gonna close this final session of the ASC. Art, do you want to say anything?
Yeah, again, I'm just from my heart to Lance and Peter. I mean, they essentially. I was involved in a modest way in the trenches, but these guys are at the helm. They're at the pirates on the ship, navigating the waters, and they essentially put on 2 conferences. Not getting paid for it. Just amazing, and such a well done conference. So my hat's out to them, my heart's out to them, and I can't wait to see you guys and everyone else I normally rub shoulders with and elbows with. And I'll put one more plug in for 2022. It's going to be in Honolulu. It's going to be 2022, and boy, I hope it's. We're planning for an in-person event, and we're going to have a lot of fun.
I wore my Hawaiian shirt in honor of 2022 Hawaii ASC.
Yeah,
just for you.
I was going to wear it, but then I realized this is recorded, and someone later on like, what is this guy wearing a Hawaiian shirt? What is it? Does it mean something? So So just, no, not tonight.
Proxy for you. All
When I
right.
get home, I'm putting my Hawaiian shirt on, and if I have anything piratey, Lance, I'm going to put that on too.
Yeah, we'll load up the ship in the cannons and start sailing her west from Tampa Yar and show up in Hawaii in a couple of years from now.
See you then.
See you
All right.
then. We'll be riding the wave.
All right. Thanks so much.
All right. And I would like to declare the 2020 Applied Superconductivity Conference as closed. I thank everybody for their support. This has been a wonderful conference. I think it exceeded our expectations when we put this on. And I hope to see everybody at the after party. Please check the links. Thank you very much.
Thank you.